All right. Good morning. Thank you. We have a nice sun outside. It would be nice to go out and play soccer rather than doing this, right? I know. If you have the homework, you can bring it in. Here there is the sign sheet. If you turn in the homework, it counts as attendance. So you don't have to sign this one. Even if you submitted the homework electronically. It's just an interaction. So if you send me an email and you write there, your class stinks, this counts as an interaction. So I count you as present and attending the class. And if you really want to sign this one, be my guest. All right. So, before we continue the material, we are catching up nicely. Is there anything we should address? More about the organization. Homework, assignments, teaching assistant, email submission, pen name. All right, don't be shy. If you need it, we talk about it. So, what did we do last time? Briefly. We talked about sequences because a sequence is a discrete structure. We learn about the denotation. As always, we are concerned about denotation. We saw some application of sequences, one of which is summations. Is everyone clear with the notation? This is the first step. You understand these two lines, what is written here. Now, what is the problem with the summation that we typically solve? Closed forms, thank you. This is the keyword I was looking for. And so, we have a summation like this line, where you have an index that goes up to n, and we want to find an expression that gives the value of the summation, and this expression is made of familiar operations, simple operations like addition, multiplication, power, logarithm, whatever. How do we do this one? How do we solve this problem? We have a couple of theorems, and I think I pointed you to a page where there are hundreds of these. We just pick two and we learn those two as example. And if we have an expression like this one, which is neither of the one of the theorems, we try to massage it in order to go back to forms that we know the closed form. In particular, we have one which is Gauss. We discussed how this is proven. We did it by induction, and we did it by a less formal method, which is very understandable. After this, we look at other sequences that we call strings or words. We said that these are interesting because when we describe languages, particularly programming languages, we use these notions. There is a notation. There are some operations that we do with strings or set of strings that when you will study compilers, you will use extensively. In particular, we saw a union, product, and closure. We saw a bunch of examples. They are below here. There is nothing complicated or creative in doing this. It's different from finding the closed form of a summation where you need some creativity, you need some idea. Here there is nothing of that, you just put the things together. Everything is very mechanical. And in fact, when you will use this for compiler, for example, all this will be done by a computer. Computer will do operation this kind without any problem. Sequences are a key structure of many programming languages. In some languages they are called a list, in some they are called arrays, in some you build yourself, like a linked list. And so we look at an inductive definition of these structures that makes it very easy to manipulate them with the computer. We saw a bunch of examples of recursive function. Just to remind you, the typical recursive function on sequences is if the sequence is empty, do such and such. If the sequence is not empty, do something for the head, recur on the tail, and now you have these two pieces and put them together according to whatever the function is computed. And we saw a bunch of examples. You should have all this clear. I'm just refreshing your memory. There is a question. Ask if you feel that you need one more example, ask for an example. All right? The next use of sequences is with induction. Here the sequence is the natural number 0, 1, 2, 3, 4. And the problem is to prove some property holds for every natural number. Of course, you cannot do it for the first, the second, the third, and so on, because you never finish. So we have this machinery that we call proof by induction. And how does it work? You prove the property for 0. This is called base case. Then you assume the property for some k greater than or equal to 0. And on this assumption, you prove it for k plus 1. Basically, you assume it for 1, and you show that if for this one is true, it's true for the next. No matter what 1 is, no matter which one is the one you pick. And so the intuition says, look, then because you prove it for 0, then it's true for 1, because it's true for the next. Now it's true for 1, because of this property, it's true for 2, and so on. And so we agree that if you do these two steps, the base and the induction, it's true for all of them. Again, we saw a few examples. We said that there are some variations of this. And the variations are one that instead of starting from 0, you start for a number a little bit bigger than 0. Maybe 1, 2, 3, whatever it is. Why? Because for some problems, the value 0 is not interesting. I think an example was if we want to prove something about a polygon, whatever is the number of sides, the smallest polygon has 3 sides. So we are not proving for 0, 1, and 2 because it's not a polygon. The minimum you can is 3. The other one is that instead of assuming for k and proving it for k plus 1, you assume it for k and all the numbers that comes before k. All of them, up to k. And then you prove it for the next. Here, we show an example where both are appropriate. And I think it's down here. Is this one here that I was referring to. That if you want to make any postage greater than or equal to 12, You can do it with stamps with denomination 4 and 5. If you have as many as you want stamps, 4 cents and 5 cents, you make every postage greater than 12. And so here we start at 12. Why we start at 12 and not at 11 or 10? Say it again?
We said at least 12. We don't care about
Right, but why don't we say at least 10?
Because it doesn't work for 11.
Fantastic, because it's not true. So the first that is true is 12. And in the proof, when we do the proof of this one, when we have to prove it for 85 cents, we assume it for 84 and 83 and 82 down up to 12. We say if it is true for all this, then I can make 85. And now, if you can make up to 85, you can make 86. And if you can make it up to 86, you prove it for 87. And so on. So far so good? The last thing that we saw, I think, was inductive definition of sets. Inductive. If you have a small set, you can write all the elements in the set, so I can tell you what is the set by showing you all the elements that are in the set. If the set is infinite, you can't do this because you'll never finish writing them. So we do it in a different way. How do we do it? We have this inductive definition. We have 3 points of the inductive definition. One is the base case, where we say a handful of elements are in the set. We write them there. Then I give you a rule, and I say, look, if you find such and such element in the set, then this other element in the set as well. And then we say, no hanky-panky, no miracle. The only way you find an element in the set is either from the first point or the second, from the base or the inductive. There are no other elements there. And so, I don't remember if you saw examples of this or not. No. So, we'll do it now. I want to find an inductive definition of the even numbers. Alright? So, first, let's write a few even numbers to make sure that we are all in sync. The even numbers are positive, I take 0, 2, 4, 6, dot, dot, dot. And so here, what I really want is to get rid of this dot, dot, dot. So, any idea? I say, look, point 1, this is the base. 0 is in the even number that I write in this way. Alright? Very easy, is a definition. Then I say, look, if x is an even number, then x plus 2 is an even number. And so now I can argue that these are all and only the even numbers. Because I have 0 there, what I also have. By the rule I have 2. Because I have 2, what also do I have? 4. Because I have 4, I have 6, and so on. So this is an inductive definition. So let me make another example here. I have a set S, and I give you this inductive definition. 4 belongs to S. If x belongs to S, then x plus 13 belongs to S. Alright? And so now I give you a number and I say, is 100 in S? I put a question mark because I don't know if it is true or false. How do we solve this one? Yes?
100 minus 4 divided by 13.
Say that again?
100 minus 4 divided by 13.
Maybe, but here I would like to do it brute force using the inductive definition, because we want to practice this.
Add 13 to every number coming up through 4.
All right, so I think you got it. You say, look, I have a 4 there, right? Because of 4, I have a 17, right? Because of 17, I have 30. Because of 30, I have a 43. And I keep it going. At some point, oops, you are not seeing it entirely. At some point, either I hit 100 or I go over. If I hit 100, I got it. I can say that 100 is there, because it comes from the base in the roots. If I don't find it, I say that 100 is not there. Is there any other way to do this? Still using the inductive definition of a set. Then we use the clever definition that is
Take 100 and minus the
fantastic. We go backward. So we start at 100 and say, well, 100 is there if and only if 87 is there. Because the only way I can get to 100 is something plus a 13. That something has to be 87, right? And so now I have a problem which is a little simpler. 87 is there if and only if, you see, I cannot even do subtraction. If a 74 is there, and you move backward, then at some point, either you hit the 4 or you don't. If you hit 4, 100 is there, and if you don't, it's not. Now, the clever method, in this case, works, but not always. It says, look, divide 100 by 13. If the remainder is 4, means that you get the 4 adding 13. If the remainder is not 4, then 100 is not there. Now, I don't know what is the division of 100 by 13 and what is the remainder. But we can do it with a calculator and find it. All right? So, we have a couple of examples here. One is the odd number. Try to do it, don't read it there. I'm putting the solution there now because we had this agreement a couple of lectures ago. But I want you to try to do it without looking at the solution. Find an inductive definition of the odd number. First, you should write the odd numbers to make sure that you know what you are trying to do. I know, it's trivial, but it's a good way to start because it suggests already a number of things. Yes?
We're doing inductive proofs. Can we use complex things like GCD or Mon? We're doing inductive proofs.
Are we talking about inductive proof or inductive definitions?
Definitions. Either one.
When do you use a model?
And you could use it for the evens and the odds as well.
I don't know, you use it when you need it. I don't have a formula that says, probably I'm going to give you problems which are not much more difficult than this. Never to use, I mean, you give me a suggestion and I keep it in mind, but probably
I was just asking.
I'm just joking. All right, who has a definition of the odds? This should take you seconds to do this. Yes?
One is numbers of the odds, and X is in the odds, and plus 2 is in
Fantastic. Can you do the powers of 10? An inductive definition of the powers of 10? First, we have to say what are the powers of 10. You should write them down. And then looking at that, probably you get a hint how to do it. You want to do it?
One is in the power.
Well, that gives the people a few seconds to do it, and then, yes, I'll let you do it. I love your team sweat.
Thank you.
All right, you want to tell us?
I think it's 1 is in the power of 10, powers of 10.
1 is in the power of 10. Perfect. Why? Can you tell why?
It's 10 to the 0.
10 to the 0. Very good.
And if x is in the powers of 10, then 10 times x is in the powers of 10.
Fantastic. 10x. Very good. All right. Can we try an inductive definition of even length string over some alphabet? The alphabet can be ABC. It's not there. Because I want you to try without looking at it. Even length string. So, for example, if the alphabet is ABC, AB is there because the length is even, 2. But ABC is not there because the length is 3. 100C is there because 100 is even. But 101 is not there because it's not even. Try to write it. I'll write it here and then we compare. Oops. Did we look at it? I wrote it in this way. A is my alphabet, and so lambda, the empty string, is in S. Let me write it better here. So A is my alphabet. Yes, thank you. I said the lambda is in S, the empty string. Why? Because the length of this string is even. 0 is an even number, right? Now, this is the base. The induction is if some string L is in S, then XYL is in S, where X and Y are in A. It's just a way of writing. You could have written where X is equal A or B or C, and Y is equal A or B or C. How do we test this one? We want to make sure this is right. How do we test it?
Write out strings and see if they fit the rules.
Right. Very good. We write a string. A string that is there, for example, is A, B, C. Right? I think this should be in S. Can I get this string with 0.1 and or 2? Yes. I start with lambda is in S. Because lambda is in S, BC lambda is in S, but BC lambda is just BC. Right? By this rule, when X is B and Y is C. And then, because of this one, ABC is in S. Why? When BC is L, A is X, and Y is X. Was there a question? Answer. Good. All right, let's do one more, and then we move on. I want an inductive definition of all the pairs, X and Y, such that X is less than or equal to Y And x and y are natural numbers. So first, should we write a few elements in this set to make sure that we understand it? All right. So what do I find there? Do I find there 1, 2, the pair? Yes, because 1 and 2 are natural and 1 is less than or equal to 2. Can I find there 3, 3? Yes. Can I find there 7, 1? No. All right, we got it. So how do we describe inductively this? Yes?
Well, you start with a base of 0, 0.
0, 0. Right. Somehow we always start with the smallest, right? When you talk about the strings, we take the empty string because it's the shortest. When we talk about even and odd, we start with 0 or 1 because these are the smallest. And then we try to build the bigger and bigger. And so how do you build bigger and bigger?
Then you say if the pair xy is in the set,
Yes?
then by the rules of less than or equal to, you say that x, y plus 1 is in the set.
Fantastic. So let me write it as we go along. So we say 0, 0 is in my set. Then we say if x, y is in the set, then what do you want to put there?
X, y plus 1.
X, y plus 1. Yes?
And in addition, x plus 1, y plus 1.
All right. Then and x plus 1 and y plus 1 are in the set. Should we test this one too? Yes?
If you want to get out of your base case, would you want to say like x is max, since your base case is 700? If it's 0, 0, is it considered the same value?
Well, x and y are any elements. So they can be equal, they can be different.
It's more ambiguous.
I'm sorry?
I was just thinking it's more ambiguous that it's less concretely right the base case.
Yeah.
We want it to be as general as possible, so you're using this to define everything.
Right. We want to be as general as possible. So, yes, I agree. Yes?
Can you replace 1 with like n or something? Because, 2 and 3 is just as true as 2 and 12. 2 is less than.
Right.
So like, wouldn't you want to get rid of the specific?
So, but now, yes, you could say for every natural number n is there. You could do it. Now, with one rule, you do everything, right?
Just
Yes.
more general.
I'm not sure.
To replace the 1.
I'm not sure. If you have to write a program on this, maybe one step at a time is, yes?
Isn't the idea of doing inductively then you'd be able to say like 2, 3 is in the set, 2, 4, 2, 5, 2, 6.
Yes, but what you said is not wrong, so. All right, so should we test this one too? Yes?
So it's not a full inductive, like proofs to be able to start outside, to be able to write out everything in theory if we had a
Yes.
family law permission. So if it's something you say can, that's ambiguous, so we need to have something that actually has a definite beginning and then step by step all the way.
Right, so an objection could be that n is an infinite number of rules because you have the rule for n equal 1 and 2. We may not want it or may be difficult to manage. But I think that I wouldn't consider this wrong. So let's test this one. Let's see how you get 2, 2 here. You must be able to get it, right? So where do we start? Only one place, 0, 0. Then which rule we apply? We have to apply the second, right? We get 1, 1. Then we apply the second again. We get the 2, 2. Right. Now let's see 2, 3. We start from 0, 0. Which rule we apply? x y plus 1. All right, so we get what? 0, 1. And then
And then do the
twice the second, right? But there is another way to do it. We can get 0, 0, 1, 1, 2, 2, 2, 3. That's perfectly fine. We don't have any problem with this, except if you're writing a program. If you're writing a program and you do something like this, you have two ways to get the 2, 3, right?
whichever possible.
Well, just make sure that if you get there twice, it's not a disaster. If you get there twice and everything is fine, no problem. But if you want to count, say, how many times something happened, and you get there twice, and you may count it twice as much, this may be a problem.
And so are you starting from 0, 0 every single time? Or can you build up from
Yes.
previous input?
Well, now if you already know that the 2 is there, then you can start from 2 because you already know. But to get that one, you start from
But if
0
your
anyway.
if your analogy is a program, then you're not going to have like a trillion if statements.
Right.
Okay.
So typically, when we work on this one, you can expect two kinds of problems. You see what are the two kinds of problems? Because probably you are going to find both in an exam or in a homework. What are the two different problems that you have here? One, I give you the inductive definition, and then I tell you whether some element is in the set. All right? The other one, so in one case, I give you the inductive definition and you have to find the set. In the other one, I give you the set and I ask you, what is the inductive definition? So one of these two problems is much more difficult than the other. Which one is it? Right. If I give you the set and I wanted the rule, you have to be creative. Right? You have to invent which is the base case. How are the rules so you get added from you have to invent this. But the other one is incredibly mechanical. I give you the rule, you just like a computer apply the rules and you determine whether an element is there or not. Yeah? All right. Done. Last point of sequences. A recurrence relation. We study sequences in part to understand the running time of a program. So let's see how many people remember what the running time of a program is. Here I'm waiting for a keyword. What is the running time of a program? A function. Thank you. You made my day. All right. So the running time of the program is a function. What does this function take and what does this function return? Maybe someone else want to tell us. Fantastic. Takes the size of the input of some algorithm, right? Just to recall your memory, if we are sorting, how many elements there are? Because we understand that the more elements you have, the more it will take to sort them. And outputs what? A number of steps. Can you be more precise?
A number of instructions or a number of operations that happen on
The number that one operation there that you pick, whatever you want in your algorithm, the number of times that that operation is executed. And of course, you have to pick an operation that the more you work, the more you execute the operation. Otherwise, it's not significant. It's not representative. Very good. So, if your program is iterative, you do an iteration with a loop or with a for, with a while loop or with a for, typically you get a summation. if your program is recursive, you don't get a solution. You get something which is called a recurrence or recurrence relation. And so now we are learning this device, how to solve a recurrence relation, because we are going to use it to find the running time of a recursive program. And the recurrence relation, as the name says, is a recursive function. So first, let's see a few simple examples. Then I make an example with the running time, so you see the big thing. So here is what is a recursive relation. Is a function that I denote by r. The argument of this function and the argument of other functions here, I use an index rather than putting it between parentheses, because they have only one argument, and in this way I save the parentheses, so supposedly it reads a little bit easier. And so the function for 0 is some other value b for 0. And the function, when the argument is n plus 1, where n is a natural number, I write it n plus 1, so 0 is excluded there. You can, no matter what n is, you cannot have 0. Is what? Is some coefficient a sub n times the value of the function for the number below, for the predecessor, plus some constant. Alright? So here again, I wanted this as a closed for. So basically, you use n and maybe those a's and b's in your closed for. So you know it. So first, let me pull up a spreadsheet and see this example. Look at this example. This example, b sub 0 is 1. Yeah? A sub n is 1, no matter what n is. And b sub n is n. You see? So let's compute it and see how it looks like. All right, so first let me put here 0. These are the inputs, equal the previous plus 1. Let me make this a little bit bigger. All right, no surprises. Now, let's look at this one here. When r is when the argument is 0, the result is 1. So this is n, and this is r of n, because here I don't have the index, I write it in this way. So here is 1 by definition, by this rule here, all right? By definition. The other one, the value of this one is what? How do I compute it for all this? Is the values of the previous one, which is this r sub n, plus n, plus n is the one before this one, because this is n plus 1. So is this one here. Yeah? All right, we see that there is not so obvious those numbers, right? So now, the problem with this one is that to compute, say, 46, I need 47. If for whatever reason I delete that 37, I lose that 46. Here, deleted, everything below is bad. All right? So how do we solve this one? the technique is similar to the summations. So let me write here because I need to look at both at the same time. Here I have R sub 0 is 1, R n plus 1 is Rn plus n. Yeah? So, I do it starting from 0 up. Some cases you can start from n going down. It's more or less the same. You can try a few and see which one you like the most. So, R0 is 1. R1 is what? R0 plus 0. Yeah? R2 is what? R1 plus what? R0, which is 1, plus, sorry, R0, which is 1 plus 0, plus what? 1. All right, I mess around. Let me restart. I'm doing too many things at the same time. So, R0 is 1. Yes? R1 is what? R0 plus 1, which is 1 plus 1. Yeah?
It's 1 plus 0 because
Yes, thank you. All right, R2 is R1, which is what? Sorry, plus 1, which is 1 plus 0 plus 1. Yeah? Thank God I am on track. R3 is what? R2 plus 2, right? Which is what? 1 plus 0 plus 1 plus 2. You with me? All right, so now I write some dots and I make a small miracle and I guess what is Rn here in that form. Who helps me make the miracle? What is this Rn? Is 1 plus 0 plus 1 plus 2 plus what? Plus n. Well, I say is n minus 1. Why? Because look, when here I have a 2, the last is 1, right? When I have 3, the last is 2. So when I have n, the last is n plus 1. So basically, this one, let me write it where in a line, is 1 plus 0 plus 1 plus 2 plus... Thank you. Minus 1. This is Rn nicely written. You with me? Now, these dots, this is called an inductive inference, which is a fancy way to make this is a lucky guess, or maybe an educated guess. Yes?
When you're doing the base case and then you kind of
Yes.
the second condition, you use n plus 1 and then n. So why in the bottom is that not Rn plus 1 equals 1 plus 0 plus 1 plus 2 dot 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 n?
Because if you look at that one, this is 1 biggest than the n. In the second rule, we have Rn plus 1, and you add n. So what you add is 1 less than the index. Yes?
that's fair.
All right. So now I have to solve this one. You should be able to do it. Yes. So this is Gauss. This is summation I from 0 to n minus 1 of I. Yeah? All right, so what is this? This is n minus 1 times n divided by 2. Yeah? And so this one is 1 plus n minus 1 times n divided by 2. We can massage it, but I'm happy to leave it this way. So now, how do we know whether we got this right? Well, we put this in the spreadsheet and we look at the two columns. So here, I put the closed form. Yes, thank you. So the closed form will be 1 plus, oh, sorry, I have to put equal 1 plus n minus 1. So this one will be this one minus 1 times n, which is this one, divided by 2. Da-da! As you can see, the lines are the same. The way they are computed is completely different. This is a closed form where I do addition, multiplication, division by 2. The other one is recursive. If you look at this one here, this one says, look, is the D12, which is the one above, plus a C12, which is this one here, which is 1 less than this one. So the big difference is now, if I delete these two, on the recursive side, everything is lost, down. On the other side, no problem. I just got rid of that one, but everything else is there. This is the reason why we understand better this other one than the previous one, right? So, you may think that the inductive inference is difficult. It's a small miracle, and so on. Not everyone can make a miracle every day. But there is a program that does it, so it's not a big miracle. Computers don't make big miracles. And is this solver here? Let me get the network, if I can. I'm always in trouble. I don't see any network here. Let me wait a second. No way. Am I the only one having network problems here or not? I'm not the only one. All right. It's not coming. Let me give it another try. Second one. All right, I got it. Let me go to this solver. All right, so here there is a link that says all right, here it is. So let's do the one that we just did and see whether this system. So here is xn. The function is called x, and so here we said xn was equal to what? X n minus 1 plus n minus 1. You agree? Oh, sorry. This is xn. We had it with x of n plus 1. All right? And the initial condition was x of 0 was equal to 1. Yeah? Solved. Here it is. And of course, it's not written as nicely, but this is exactly the one we had. Is n times. So this is half n, 1 plus half n.
They just distributed the
Right. Right. Now, this is very interesting because, of course, the system could write this in a much more readable way. Because it's smart enough to do the inductive inference, which is more complicated than this. But they didn't pay the time to. So, if you want to practice, you can practice and then you can test it with a spreadsheet the way I did. Or you can come here and get the system to solve it for you. And you can practice. So, should we do another one before the break? Let's do another one before the break. All right. Should we do this one? This is much more complicated. So, let me bring this one up. So this one is R0 is equal 3. And Rn is equal to Rn minus 1 plus 3. And because here I write it in this way instead of Rn plus 1, I want to say n greater than 0. Because the case 0 is already done by the one above. So, how do we do this one? We write a few, and I again start from 0. You can start from the other side, it's the same. So, R0 is equal 3. What is R1? Is R0 plus, is twice R0 plus 3, which is 2 times 3 plus 3. You with me? Help me because I can't balance my checkbook. Doing this is difficult. R2 is equal to what? 2 for all this one, which is 2 times 3 plus 3. Yeah? Plus 3. Now, I heard someone before saying 9. It's not a bad idea to put there a 9. But at some point I know I have to do the miracle, right? So, if I leave it in a way where I see how many 2's and how many pluses and whatever, maybe a little bit easier than that I see the pattern. So, R3 is equal to what? R2, which is all this one, 2 times 2 times 3. Sorry, I have to be careful because if I blow this one, 2 times 3 plus 3 plus 3 plus 3. Did I get it right? Yeah. So now I have to figure out to see what's going on. So this one is 2 square times 3 plus 2 times 3 plus 3. This one here. Yeah? Yes? And here I would put 2 to the 1, and here I would put 2 to the 0. You with me? So this one would be 3 times 2 to the 0, 2 to the 1, 2 to the 2 added together. So now let me do this one. Here is this one times 2 plus 3, so this will be 3 times 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. Yeah? You see? So now let's write Rn. What is Rn? 3 times summation for I that goes from 0 to n, 2 to the I. Is 3 times the summation for I from 0 to n, 2 to the I. And so, what is this part here, the summation? We have a formula, right, that we saw earlier today. Let me bring it back so we'll refresh the memory. Is this one here? Oh, sorry. Is this one here? You see it? Where A is equal to. And so this one will be 3, 2 to the n plus 1 minus 1 divided 2 minus 1. Yes? Which is 3 times 2 n plus 1 minus 3. Now with the spreadsheet, I could put the recursive, I could put the closed form, and check whether for the first 10 or so they are the same. Or I could use the solver, put that one and see whether the solver is able to do it. Alright? Any question about all this?
For R, so 3 would have to be 2. Wouldn't be 3 or 2, not 3, but for R, so 4 goes up to 2. 3, not 2, 4.
Well, so let's look for 0, which is very easy. For 0, we have a 3, 2 to the 0, which is 1, right? And for 1, now we have 2 to the 1, which is 2, times 3.
Okay.
So I would say that this looks right to me. All right, let's take 10 minutes.